Hello all. So the plan was to go over the most recent October 2025 papers, but because it's gonna take some time to work on this, and because I have the tendency to postpone things and stuff like that, I will go over a past paper from January 2024, and this is a Unit 1 paper. This is the first time I'm doing a Unit 1 past paper. The plan has always been to incorporate Unit 1 lessons and past papers as well as Unit 2 and Unit 3 papers and lessons in this channel, but I haven't got around to do that. But anyway, it's good to start from somewhere. So let's do the January 2024 paper and let's dive in. Okay. Oh, and I also uploaded a few lessons on Unit 1. For some reason, they don't get a lot of viewership, but I don't know. I plan to finish the Unit 1 lessons at some point. I mean, hopefully within this month. And then I will start the Unit 2 lessons. But I feel like people find the past paper walkthroughs useful as well. So let's do the past paper. All right. So first of all, before we start, Unit 1, in Unit 1, you have an hour and 30 minutes, okay? And as I said in past videos, maybe some of you will, never watched Unit 4 or Unit 5 papers and so on. In those videos, I always say that the rule of thumb in the A-level exams, but also in AS level exams, is that that is awarding 1 mark should take you about a minute. If a question awards 10 marks, it should take you about 10 minutes. This is a rule of thumb. I mean, if a problem takes you 3 minutes and it's a 1 mark problem, that's fine, because some other problem might take you 30 seconds. But you have to keep in mind, on average, a 1 mark question should take you a minute, a 10 mark question should take you 10 minutes, okay? I mean, for time management, all right? And the other thing I say for exams is that if you don't know a question, skip it. Don't spend time. I mean, if it doesn't occur immediately, skip it and work on other questions that you already know the solution, okay? And you can always come back to a question that you didn't know, okay? Don't waste time, because there is not a lot of time, okay? So let's start now. Question 1. Which of the following is an SI unit for stress? Okay, you can always go to the back of the paper and find, they give you most of the formulas you will need. I know the definition of stress, but I just want to show you that even if you forget, you can go to the back of the paper. Stress is related to materials, so you skim through the equations they give you and you find stress, okay? So stress is force per area, right? Which is the same as pressure, but pressure is a different kind of thing. So, all right, so stress is force per area. The units for force are newtons, and I use square brackets for units, okay? The units for an area is meter squared, but newtons are not fundamental. In fact, 1 newton is 1 kilogram times meters per second square. How do we know that? Because force is mass times acceleration. So the units for force, which are newtons, are equal to the units for mass, which are kilograms, and the units for acceleration, which are meters per second squared. Then acceleration itself is defined as the change in speed per time. That's why meters per second squared. Whenever I use square brackets, that means that I'm dealing with the units for that physical quantity. All right. All right. I mean, I've been talking too much in this video. I don't know why. So, okay, newtons are kilograms times meters, and then second squared. But we have the meter squared from before, so meters gets cancelled. I feel like I messed up something. Did I? No. Okay, which is the correct answer? It's D. Oh, Okay, see, I mean, this is what happens when you're not fully prepared to make a video. But anyway, newtons per meter square was there all this time, and I kept working. Okay, what I actually did, which was not asked in this question, was to break derived units down to base units. Okay, so, and the base units again are, I talk about this in past videos probably. So kilograms, meters, seconds, amperes, candelas. What else is a fundamental unit? Kelvin for temperature. There are 7 of them. I'm missing one. Come on. And moles. Okay. So these are the fundamental units, base units. All right. Question 2. Which row of the table contains vector quantities? So acceleration is a vector quantity, momentum is a vector quantity, and weight is a vector quantity. So option A is correct, actually. Okay. Another thing about section A of unit 1, unit 2, and so on is that you can eliminate options. So in this example, for example, in option B, you see time. Time is not a vector quantity. And then in option C, you see mass. Mass is not a vector quantity. And then temperature is not a vector quantity. All right, so all 3 options are wrong. And you can easily derive the correct one. All right, 3, a spring is stretched by applying a force of 3 newtons. The elastic strain energy stored by the spring is 0.04 joules. Which of the following expressions gives the extension in meters of the spring? Okay, so force is k times x, right? So k, the spring constant, which is not given, is force per displacement, right? Is that correct? Yes. So 3 over x, because it's 3 newtons, right? And then, where do we need this? I actually don't think we need this. I'm sorry. Let's try a different way. So the elastic, let's call it W elastic, strain energy is 1/2 F times delta X, right? And they are asking for the extension, so delta X is equal to the elastic energy over the force times 2, so 2 times 0.04 over the force, which is 3. And the correct answer is A. Okay, and I think they give you this formula for the force, for the energy in the back of the paper. Let's go see, let's go check. Yes, they do, this one. Okay, actually let me erase this. Okay. Okay, so let's go back to section A. I'm sorry for moving too slow. Okay, we worked the first 3 questions. Let's do problem 4. Okay, question 4. A cyclist moves along a horizontal road at a constant speed. She then moves at the same speed up a hill with a constant gradient. Which of the following graphs shows how the power output P of the cyclist varies with time? Okay, so the key here is that she moves at a constant speed on a horizontal road, and then she keeps moving with the same speed up a hill. Okay, so the power output is given by okay, there are several definitions. Let me go see in the back of the paper which ones they give you. So power, okay, they give you only those 2 quantities. Do they give you anything else? They don't. Okay, so okay, let's go here. So so work done per time. So the work done though can also be written as force times the change in position, so the displacement, and then we can write delta t, can convert that to delta t. So the power output is F times V. Okay, this is something you have to derive though. I mean, they don't give you this, but since the speed is constant, okay, so initially, and the force is going to be constant, okay? So initially she outputs some power, okay, which is constant. So these three are candidates for the correct solution, okay, because she has, she does have to output some power, right? So this is wrong. I mean, option A is wrong because the power cannot be 0, right? And then the power she exerts when she goes uphill should increase because the force she has to output should increase, right? Because she has to do work against her weight, okay? But the velocity remains constant, and therefore the power should increase and also be steady. So this gets eliminated because the power cannot increase with respect to time. This also gets eliminated. So the only correct answer is D, okay? I hope this makes sense. I'm trying to think internally now whether there is anything else. So, okay, I mean, if you think of the cyclist on the road, okay. Okay, so that's the cycle, I guess. Okay, something like this. So when she goes on a constant road, she exerts some force on the pedals, I guess. And the velocity is constant, therefore the power is constant and positive, right? But then when she goes uphill, she has to increase the force she puts on the pedals, right? Because now, if that's her weight, then there is a component parallel to the displacement. The displacement is in this way, along the direction of the heel, right? So there is this component of the weight that is pushing her down. So the force has to increase to counteract for this component of the weight. Therefore, the force is still constant, but higher than before, right? But the velocity is constant, so the power increases, okay? I hope this explanation makes sense. If it doesn't, please comment and I will come back to you and hopefully provide a better explanation. All right, question 5. A student dropped a table tennis ball. Okay, the ball fell for time t and had velocity v just before it hit the ground. The student used the equations of motion to calculate t and v. These equations ignore air resistance. Which of the table shows how the actual values compare with the student's calculated values for t and v? Okay, the table shows how the actual values compared with the student's calculated values for t and v. Okay, so because there is air resistance, okay, I mean, you can picture a ball falling down, okay. Okay, so the student ignored air resistance. For those of you who played table tennis, you know that the ball is really light. So if you drop it from a height and you use the SUVAT equations without, ignoring air resistance, your calculated time is going to be less than the actual time. So options A and B are immediately eliminated. And then the velocity is going to be less than the one calculated, right? So C is the correct answer, right? Because of the air resistance, the velocity is gonna be less than what you expect from the SUVAT equations. Question 6. A length of string is attached between two vertical posts. A burst of weight W stands on the middle of the string, causing tension T in the spring. The string makes an angle of 80 degrees with each post as shown. Which of the following expressions is correct? Okay, so this thing is in equilibrium, right? So there must be a component of the tension that counteracts the weight. Okay, so I'm talking about this direction. Actually, okay, I mean, the length of this vector should be the same as the length of this vector, but okay, I mean, you get the idea. Okay, but we have two tensions, this one and this one, so we have 2 times the vertical component of t. And which one is the vertical component of t? This, if this angle is 80, this is also 80, right? So this component is going to be, let me transfer this there so I have space to write. So we have 2 times t cosine 80 degrees. How do I know it's cosine and not sine? I think I mentioned it in previous videos. You can go check. Maybe I will have a link for you in the description if I find the video, because at this point I have too many videos and I don't remember where I said things. But anyway, when the angle, the way I mean the rule I have in my head whenever I analyze forces is that when the angle touches the vector, okay, so in this case the 80 degrees angle touches the vector, right? Then whenever it's touching, it's a cosine. Whenever the angle is not touching, so for example this component would be t sine 80 degrees, because the 80 degrees angle does not touch this component vector. Okay, I hope this makes sense. So anyway, to go back to our problem, 2t cosine 80 degrees should equal the weight, right? So t is going to be equal to the weight over 2 times the cosine of 80 degrees, and that's the answer. This is option C. Okay. Question 7. A force, so a force is applied to stretch a spring. The graph shows how the length of the spring varies with the applied force. Okay, which of the following gives the stiffness of the spring? So okay, this is easy. Force is kx, right? Actually minus, but okay, we are taking the magnitude, I guess. So we have the force here and the length x here, therefore it's the gradient, right? So the gradient is equal to k, and you can see this from the linear equation over here. Okay, so C. Okay, this was easy. A solid cube of weight W is made from material with density ρ. Which expression gives the length of each side of the cube? Okay, the density is mass per volume, right? What's the volume of a cube? X cube, right? So x cubed is gonna be let me see, mass over density, right? So x is the third or cubed root of mass over the density, but they give us the weight, right? So we have to multiply with g, so m times g, and if we multiply the numerator by g, we have to multiply the denominator with g as well, because they cancel, right? So let me go back. Okay, here and here. Okay, so yeah, that's the answer. I mean, weight, so it's the cube root of weight over ρ times, oops, okay, the cube root of weight over ρ times g. So it's option, which one? Wait, D, right? Yes. Question 9. A force is applied to stretch 2 wires P and Q until the wires break. Each wire is made of a different metal, I'm sorry. The stress-strain graph for each wire is shown. Which of the following statements is correct? P has a greater breaking stress than Q. The breaking stress of P is this one over here, right? The breaking stress of Q is over there, which is higher, so A is wrong. Let me erase this, okay. Option B says P has a greater breaking strain than Q. Okay, that's the breaking strain of P, and the breaking strain of Q is higher, so B is wrong. P has a greater yield stress than Q. The yield stress is where the material changes from elastic to plastic deformation, right? So P, okay, the yield strength for P is this one, and the yield strength for Q is this one. So P does have a greater yield stress than Q, and that's the correct answer. Okay, so I'm gonna put it there, yield stress, the material becomes deformed plastically. Which means plastically means it cannot go back to its initial condition. I mean, it kind of starts breaking, okay? And let's also read the option D. P has a lower Young modulus than Q. That's wrong because the Young modulus is the gradient of this graph, right? So P has in the linear region, it has a higher gradient, okay? So that's wrong. Okay, that was a good problem. Let's go to question 10. Okay, question 10. An object moves from rest with uniform acceleration for time t. The acceleration time graph for the object is shown. X is the area under the curve between time 0 and time t. Okay. Which of the following expressions gives the distance moved by the object? Okay, so the key here is that it moves from rest, and we are given the area under the curve. Okay, so the area under the curve in an acceleration time graph represents the change in velocity, right? So x is delta v, and delta v is the final velocity v minus the initial velocity u, but the initial velocity is 0. So x is just the final velocity v. Okay, and we need to find the distance moved by the object. So let's go check the SUVAT equations really quick. So I'm here again in the back of the paper like before. Let's erase this. Okay, so the SUVAT equations, we need the distance. So this is a candidate and this is a candidate, right? But this one involves time, so it's not very clever to use that. Okay, let's try this one. S is u plus v over 2 times t. Okay, in our case, u is 0, v is x, so x t over 2, right? This sounds promising. Let's go back and see. Where was it here? So yes, actually option D is there, so that's the answer. So again, S is u plus v over 2 times t. U is 0, so we just have v times t over 2, but v is given by the area under the curve, so xt over 2. Okay, hope this makes sense. Let's move on. Question 11. I guess this one involves counting, but let's see. Okay, so a student applied, I mean, counting, usually in this kind of graphs, when they give you this kind of graphs, you have to count how many squares make up for some quantity that they ask you. But anyway, let's see. By the way, this is section B now. Okay, and the first question, which is question 11 in section B, gives you 4 marks. So again, in your mind, this should translate to, okay, this should take me about 4 minutes. Okay, so a student applied the force F to a rubber band. The student measured the corresponding extension delta x as F was increased and then decreased. The graph shows how delta x varied as F was increased and then decreased. State how the graph shows that the rubber band deformed elastically. The key here is that okay, you expand the rubber band, okay, by increasing the force, but then when you decrease the force, it goes back to where it started, okay? So this is the definition of elastic deformation, right? Because if you go into the plastic deformation region, right, area or whatever, it will never come back, okay? So the answer is that when the force was removed, okay, the band returned to its original position. And you can see it from the graph, I guess. So, part B, the work done on the rubber band as F increased is greater than the work done by the rubber band as F was decreased. There is a difference in these values because heating occurred. Determine the energy that caused heating as F was increased and then decreased to 0. So this energy is actually represented by, see, I mean, in the beginning when we started working on this problem, I told you that this will involve some sort of counting. So this area pretty much represents the energy lost, okay? So I'm gonna write it down for you, even though you don't have to write it in the test, but I'm gonna write it for you so you have it. So the elastic energy is the area under the graph. Okay. So yeah, the area between the two graphs is the energy lost, pretty much, okay? Because let me erase this. This is kind of like the energy gained when you increase the force, and then when you decrease it, this is the energy gained, okay? So the difference between these two graphs is the area here, okay? So let's go count how many squares there are. Okay, first of all, let me see. Okay, this is gonna be tedious, but okay, you can measure this kind of squares. Okay, so this square has an area of, let's see, 0.5 times 0.5. So each square represents 0.25 newtons per centimeter, right? Wait, what am I saying? Newtons times centimeters. I'm sorry. Oops. I'm all over the place, guys. I'm sorry. So that squared, okay, so this is 0.5 newtons and this is 0.5 centimeters. So the area is 0.25 newtons times centimeters, okay? And in here there are about 17. I mean, this is what I have in my notes, but you can count it really quick. So 1, 2, 3, 4, 5, let's say 6, 7, 8, 9. These two can count as 1, 10, and then maybe 11, 12, 13, and then you have 14, 15, 16. Yeah, it's about 17, okay? You can count it on your own, on your free time. I'm not gonna do it because it's really difficult to do these things on the screen. So we have 0.25 times 17 gives you Let me do the calculations. I have my calculator here with me. You don't see it. So 4.25, oops, 4.25 newtons times centimeters, but then we have to convert the centimeters to meters by multiplying by 10 to the minus 2. So newtons times meters. So this is about 0.05 joules. Okay, I mean, this is the answer. Okay, moving on to question 12. In a game called darts, did they have to write that? I mean, isn't it obvious? I mean, everybody knows darts, right? Do kids these days play darts still? Let me know in the comments. Okay, so in a game called darts, metal darts are thrown towards a dartboard. The darts hit the dartboard as shown. Okay. A dart is thrown with a velocity of 15.6 meters per second at an angle of 5 degrees to the horizontal. The dart travels a horizontal distance d to the dartboard as shown. Okay, cool. Just before the dart hits the dartboard, the vertical component of the velocity of the dart is 0. Okay. The air resistance acting on the dart is negligible. Show that the time taken for the dart to reach the dartboard is about 0.14 seconds. Okay, let me use a clean page for this. So this is the component of the velocity. Sorry, this is the velocity, I'm sorry, okay? And it has two components, okay? The horizontal component, so this angle is 5 degrees. So the horizontal component is 15.6 times cosine 5 degrees. Remember what I said earlier? This angle, this 5 degrees angle, touches the horizontal component of the velocity vector. Therefore, we use cosine. So immediately we know that for the, actually, let me use a different color for the components. Okay, so let me erase this. So this is the velocity, so this is the horizontal component, and this is the vertical component, right? Now for the vertical component, we know that it should be equal to the magnitude of the velocity, which is given as 15.6 meters per second, times sine of 5 degrees. Why sine? Because the 5-degree angles does not touch the vertical component, okay? So we need to find the traveling time. So we can do that by using this information, okay? So it's a little bit of a complicated problem, but it says that just before the dart hits the dartboard, the vertical component of the velocity of the dart is 0, okay? So we can work with this component over here, okay? So I'm gonna specify here that we are working with the y axis, okay? So the SUVAT equations for the y-axis, one of the SUVAT equations that we can use is that the final velocity, let's call it y, should equal the initial velocity, let's call it y, plus a, also, okay, let's call it y as well, the acceleration in the y direction, times t, okay? What's the final velocity in the y direction? 0, because it says just before the dart hits the dartboard, the vertical component of the velocity of the dart is 0, okay? So 0 is equal, what's the initial velocity in the y direction? It's 15.6 times sine 5 meters per second. This is a 5, okay? And then okay, and what's the acceleration in the y direction? Minus g, right? Because the acceleration points downwards in the y direction, and it's equal to g, right? Which is minus 9.81, and then times time, okay? And we have a very pretty equation for time. If we solve it, we find 0.14 seconds for the traveling time. Okay, and then we can go to the x-axis and find the distance. Okay, how can we do that? We can use the SUVAT equation S is equal to u, which u in the x direction, times t plus 1/2 ax times t squared. Okay, so what's the initial velocity in the y direction? In the x direction, 15.6 times cosine of 5. Okay, what's time? 0.14 plus what's the acceleration in the x direction? Is there an acceleration in the x direction? No. Okay, so that's 0. That's great. Okay, we have a cancellation. So we find 2.18 meters. Okay, 2.18. Oops, what am I doing? 2.18 meters. Okay. Oops, they only asked for the time. Okay, for part A, show that the time taken for the dart to reach the dartboard is about 0.14 seconds. Okay, so we did that here. Okay, and did they ask for the, okay, calculate the horizontal distance d traveled by the dart. Okay, we did it, so 2.18 meters. Okay, I don't know why I was carried away. Anyway, this is the answer. Okay, so let's move on. Question 13. Okay. This looks interesting. Okay, it's a 3-mark question, so it should take you about 3 minutes. So it should be kind of easy, maybe. It doesn't look easy though. So a student has a toy called a Cartesian diver. Never heard of this thing before. Inside a sealed plastic bottle of water. The Cartesian diver consists of a tube closed at one end, okay? Air is trapped by water inside the tube as shown, okay? So there is some trapped air in that thing, and then there is water in the bottom, and it's a sealed plastic bottle. The student squeezes the bottle. More water is forced into the tube, and the volume of the trapped air decreases. Explain why the Cartesian diver accelerates downwards. Okay. So, okay, we can write the following. Okay, so this is a writing problem, I guess. So when water enters the diver, its mass increases, right? This is easy to understand, I guess. At the same time, okay, first of all, there are just 2 forces in the diver. Let me digress a little bit. So, okay, actually, okay, these forces only apply to the diver. So, or maybe we can do this. Maybe we can take this guy and, okay, so this is the situation. I transfer the drawing here, I guess. So this is what I'm trying to do, okay? So this is what it looks like. Okay, and it's there is some water, okay? So how many forces are there on this thing? It's its weight due to the water trapped, and then the upthrust due to the trapped air, right? So let's keep answering. Okay, when water enters the diver, its mass increases. At the same time, since the air volume decreases, since the air volume decreases, the upthrust decreases, right? So there is a resultant. In other words, the weight is larger than the upthrust. So, okay, so maybe you can write that as well. So the weight of water, I guess. So the weight becomes larger than the upthrust, right? Hence, there is a resultant downwards force, and the diver accelerates downwards. And that's the answer. Okay. Okay, let's move on to question 14. Let me check my notes. Give me a second. A child's slide has a vertical weight of 1.7 meters as shown. A child starts from rest at the top of the slide and moves down the slide. The resistive forces acting on the child can be ignored. Explain why the equations of motion should not be used to determine the maximum speed of the child. You should consider the shape of the slide. Okay, so I have some answer in my notes, but I want to check against the mark scheme that I have in front of me on my screen, but you don't see it. Okay. In future videos, maybe I should also have the mark scheme. But anyway, so in the mark scheme, they say the gradient steepness of the slide varies. Okay, so their answer is similar to mine. So I'm gonna write my answer. So my answer was, I mean, these are some notes from 3 years ago. That's why I hesitate. Not 3 years ago, 2 years ago. So the equations of motion, SUVAT, work for uniform acceleration. Oops. Okay. Since the gradient of the slide varies, A is not constant. Okay. So we cannot use SUVAT equations. Okay, and that's the answer. The child has a mass of 24 kilos. Determine the maximum speed v of the child on the slide. Okay, this sounds strange, right? Because they only give you the mass. How on earth are you gonna find the maximum speed? Okay, remember that the change in gravitational energy should be equal to the change in kinetic energy, right? So you're gonna be surprised by one fact right now. So what's the change in gravitational energy? mgh, right? And h is just 1.7 meters. And this should be equal to 1/2 mv squared. Okay, m cancels, so you don't need the mass. Okay, so that's I guess they try to trick you in these tests. But anyway, v is just the square root of 2 times g times h, which is equal to the square root of 2 times 9.81 times 1.7 meters. And if you use your calculator, you're going to find 5.78 meters per second. Okay. Part B. Two slides, X and Y, have the same height. Slide X is longer than slide Y as shown. Okay. A child moves from rest down slide X and reaches a maximum speed Vx. A second child moves from rest down slide Y and reaches a maximum speed Vy. The child on slide Y has a greater mass than the child on slide X. The resistive forces acting on both children can be ignored. Explain how Vx compares with Vy. Again, trick question. What's the trick? The same height, okay? Same height. What did we find here? What did I tell you? That the mass drops out, okay? So it's the same case. Doesn't matter. I mean, if you ignore resistive forces, okay, if they told you that there are resistive forces, the final speeds will not be equal, okay? There will be changes needed and adjustments, but this is not the case. So immediately you can write Vx is equal. I don't know what happened with my pen. It's a little bit unresponsive. So Vx and Vy are equal. Okay, because V does not depend on mass, and in both cases something's wrong with my pen, and in both cases delta E kinetic is equal to delta E gravity, okay? And that's the answer, right? So that, yeah, there is nothing else we need to write. So we have to move on. Okay, question 15. A student investigated small ball bearings falling through a liquid to determine the viscosity of the liquid. State the conditions needed for Stokes' law to apply to this investigation. Okay, Stokes' law assumes laminar flow, right? So we can just write that down, okay? So laminar flow, okay, laminar flow, low speeds, no turbulence, I guess, okay. Okay, part B, complete the free body force diagram for a ball bearing when falling at terminal velocity. Okay, so we have the drag force, we have the weight, okay, and we also have the upthrust, right? And the upthrust is in this direction. And by the way, this is a trick, I guess, again, because these three forces are always there, okay, when the ball is falling. And when the ball falls at terminal velocity means we have no acceleration anymore, which means that the resultant force is 0, which means that the weight is equal to the upthrust and the drag force. I hope this makes sense. Okay, let's do part 2. Student thought that the liquid she used might be glycerol. She made measurements to determine the terminal velocity of the ball bearing. The terminal velocity of the ball bearing was 0.0824 meters per second. deduce whether the liquid she used was glycerol. And they give you the density of glycerol, the radius of ball bearing, the weight of ball bearing, and the viscosity of glycerol at room temperature. Okay, so as I said in the previous question, part B, at terminal velocity, the upthrust plus the drag force should equal the weight. Okay, so let's write this down. So m times g should be equal to the drag force, which is the Stokes force, 6 pi times the viscosity eta times the radius of the ball bearing times the velocity, which is the terminal velocity, right? Should and plus the upthrust, which is the density of glycerol, times g times the displaced volume. Okay, so the weight, which is m times g, is just 4 times 10 to the negative 3 newtons. Okay, so we have that. And let's see. The Stokes force, which is the drag force, let's call it D. Okay, D is 6 pi times the viscosity, which is 0.934, and then times the radius, which is 2.3 millimeters, so 2.3 times 10 to the negative 3 meters, right? What else are we missing? Times the terminal velocity, which is 0.0824 meters per second. Yields, the drag is 3.3 times 10 to the negative 3 newtons. And let's find the upthrust, the final piece in this puzzle. So this should be the density of glycerol times G times the volume. So if it's indeed glycerol, and D plus U should be equal to W, the weight, right? So 1.26 times 10 to the 3 is the density. It's a little bit denser than water. Water is 1 times 10 to the 3 kilograms per cubic meters, okay? Times G, 9.81, times volume. The volume of displaced glycerol should be the same as the volume of the ball bearing. So that's a cube, 4/3 pi times radius cubed. So the radius is 2.3 times 10 to the negative 3 cubed. And if we carry the calculations, we find 6.29 times 10 to the negative 3 newtons. And then if we add D plus U, we find 3.97 times 10 to the negative 3 newtons, which is about the same as the weight, which is 4 times 10 to the negative 3 newtons. So true, it's glycerol. Verified. Very cool. Okay, let's move on to question 16. Why did it do this? Okay, so a skittle is a wooden object that can stand upright on the end. In a game of skittles, a ball is thrown at some skittles to knock them over as shown. This looks like bowling. I've never seen this before. If you guys have seen this or if you have played this game, let me know in the comments. Okay, please write in the comments. So the diagram below shows the ball just before it collides with a skittle. Okay, cool. Question A, the graph shows how the velocity of the skittle varies with time. The time shown on the graph starts just before the ball hits the skittle. Okay. Determine the average acceleration of the skittle during the collision. Okay, this is the velocity and this is the time. So it's going to be the gradient of this graph, guys, right? So the gradient of this graph. Why? Because that's the change in velocity with respect to time, right? So let's let's write this down. So area is equal to the gradient, which is equal to the change in velocity with respect to time. And okay, in my notes I took different points. Okay, let me try something different. So we can take this point over here and this point over here, or we can take this point or this point. Any 2 points are good, okay? But it's good to take them far apart. So no, actually, I'm gonna use what I have in my notes. So I have 2.2. So I have, for delta V, I have 2.2 minus 0.2. Okay, so 2.2 for the velocity is this point over here, and 0.2 is this point over here. Okay. Okay, I did this, I guess, because it's easier to find the time. Okay, so I was wise when I chose these points 2 years ago. Okay, so 2.2 meters per second occurs at 40 milliseconds, and 0.2 occurs at 20 milliseconds. So let's subtract those. So 40 minus 20, it's milliseconds, so we have to multiply by 10 to the minus 3. So we find 100 meters per second squared. That's a really large number. Okay. This is a 12-mark question. Okay. So let's do part B. Explain how Newton's second and third laws of motion apply to the ball and the skittle during the collision. Okay, I'm going to write my answer and then check with the mark scheme to make sure that my answer from 2 years ago was correct. So the skittle is initially stationary. Okay, stationary. Okay, as the ball hits the skittle, okay, its momentum changes by delta P, okay, during a collision time of delta T. And please write in the comments whether you can read my handwriting, because people complain about my handwriting a lot, and I do make an effort to make it better, but okay, sometimes I fail. Most times I fail because, you know, my natural tendency is to write really bad. It's to have a really bad handwriting. So anyway, okay. According to Newton's second law, let's write it N2. F is change in momentum with respect to time, right? So so a force acts on it. Okay. As the time at the same time, okay, the skittle exerts the same force in the opposite direction. So this is Newton's third law, and this is what happens. Okay, let me check the mark scheme and see what they say. So in the mark scheme, they say the ball applies a force to the skittle applies a force to the ball. Okay, we said that. Newton's third law means that the forces on the skittle and the ball are equal in size and opposite in direction. We kind of imply this. There is a resultant force acting on the skittle. The skittle accelerates according to Newton's second law. The skittle accelerates to the left and the ball decelerates. Okay, so it's a little bit different, but we cover most points. Part C. The ball is thrown again and collides with another stationary skittle. During the collision, the horizontal velocity of the ball changes from 7.2 meters per second to 1.6 meters per second. The horizontal velocity of the skittle immediately after the collision is 3.1 meters per second in the same direction as the ball. Determine the mass of the ball. They give you the mass of the skittle. Okay, so the mass of the ball times the initial velocity, which is 7.2 meters per second, should be equal to the mass of the skittle, right, times its velocity, which is 3.1, plus the mass of the ball after the collision times 1.6, which is the velocity of the ball after the collision. So 5.6 times the mass, the mass of the ball should equal 3.1 times the mass of the skittle, or mass of the ball, if we plug in the numbers, is 0.78 kilograms, which is the answer. And it agrees with the mark scheme, so let's move on to question 17. A student determined the Young modulus of a material in the form of a wire. The student used a micrometer to measure the diameter of the wire. Describe how the student should check that the wire is uniform, check that the wire has a circular cross section. So to do that, and actually this is kind of like a Unit 3 question, because in Unit 3 they ask you about practical skills. But you see how in A-level they assume that, okay, a person who is taking Unit 2 knows enough from Unit 1 to answer questions in Unit 2 that might involve some knowledge from Unit 1. Or here they ask you a question from Unit 3 to ensure that you are also prepared for Unit 3 and so on. So it's good to know all the units before taking an exam. Okay, so you can measure, the answer is that you can measure the diameter at several positions along the wire and at several orientations. Because, for example, the wire might not be completely circular. It might look more like this, okay? So this diameter will be different from this diameter, right? And so on and so forth. And also, if you measure at several different positions, because the wire is like this, okay? So you have to measure the diameter here, here, and here, say, and then at several different orientations as I show there, okay? So let's do part B. The student hung a reference wire and the wire being tested from the ceiling, okay? At the lower end of the reference wire, he positioned the fixed part of a vernier scale. The student attached a 100 grams mass hanger to the wire being tested. The initial reading on the vernier scale was 0 millimeters as shown, okay? I mean, they mean this part, I guess, okay? He added masses to the mass hanger and measured the corresponding extension delta X of the wire using the vernier scale. Cool. Part I. The student kept his feet away from the apparatus so that the masses could not fall on his feet. Explain one other safety precaution. So you need to use safety glasses. In case the wire snaps. Okay, because it might snap and hurt your eyes. Okay. Part 2. Each time the student added more mass, delta x each time the student added more mass, delta x increased by a few millimeters, explaining why he should measure delta x using a vernier scale instead of a meter rule. Okay. So the vernier scale, I mean, you can say the vernier scale can measure down to 0.1 millimeters, so it has a better resolution and smaller uncertainty than the meter ruler. Okay, and now part C. Okay, for each mass added, the student determined the force on the wire. The student plotted the graph shown. Okay. Do they ask anything here? They don't. Okay. The table gives the Young modulus for some materials. Okay, they have aluminum, brass, and steel. That use which material the wire was made from, and they give you the original length of wire and the diameter of wire. Okay, so Young's modulus is given by stress over strain, right? Stress is force per cross section, and strain is the change in length over the length. Okay, so delta x is equal to length over cross section over Young's modulus times the force. Okay, and this is exactly what they give us. They give us delta x with respect to the force. So the gradient is equal to length over the cross section over the Young's modulus. Okay, so the Young's modulus is going to be equal to the length over the gradient over the cross section. Okay, so for the gradient, I'm going to go back to the graph and show you what I did. But okay, 10 minus 2 millimeters over 14.5 minus 3.5 newtons. So the gradient is 7.27 times 10 to the negative 4 newtons per meter. Meters per newton. Okay, meters per newton. Okay, so the Young's modulus then is going to be, then let me show you. Okay, 10, so I took this point and this point. Okay, so at this point the force was about 14.5. Okay, and at that extension the force was, what did I write there? 3.5. Okay, so this is what I did. Okay, so the Young's modulus should be the length, which is 1.8 meters, okay, over the gradient 7.27 times 10 to the negative 4. And then we need the cross section. They give us the diameter, so pi times 0.085 times 10 to the negative 3 squared. So we find 109, so 109.1 gigapascals. so gigapascals, and we can see immediately that it was made of brass. Okay, and that's the answer. In case you are confused, since the diameter is 0.17, then the radius is 0. Did I mess up something? Let me see. I think I messed up something. What's something is bothering me. Okay, so 0.17 over 2, so 0.085 millimeters. So I added one more zero here. It should be okay. I'm sorry, 0.085. Okay, in case there is something wrong with the calculation, let me know in the comments, but I want to move on. You got the idea about how this problem is solved. So, question 18, a uniform door of width W is supported by two hinges X and Y. X and Y are a vertical distance L apart as shown. Okay, and they show you the door. State the conditions needed for the door to be in equilibrium. Okay, so the clockwise moment, I guess. So the clockwise moment should be equal to the anti-clockwise moments. Okay. Give the meaning of the term center of gravity. So it's the point. I'm trying to. Okay, so the weight. Let me write it this way. So it's the weight of the object is thought of as acting from the center of gravity. Okay, and that's the answer. Okay. Wow, this is a 16-mark question. Okay. Okay. Part C. The diagram shows the force acting on the door at each hinge. The mass of the door is 14.4 kilograms. The weight of the door causes a moment about each hinge. Okay, show that the horizontal component of the force of hinge Y on the door is about 40 newtons. Okay, so the center of gravity for the door is, I mean, you can draw the diagonals. Okay, so it's somewhere there. Okay, so let me raise this. So let me use a red. Okay, so that's the weight. So m times g is acting from the center of gravity. Okay, and this is w. So the weight is acting at a distance of w over 2, right? Okay. Let me think. The mass of the door is 14.4. Okay. Okay, so we can write that. Okay, they give us L, the weight of the door. Okay. Show that the horizontal component of the force of hinge Y on the door is about 40 newtons. And they give us L. What is L? It's the distance. Okay, so this is L. Okay, so the force from Y, we don't have to analyze. So force Y times L, right? Should equal I mean, if we take the moments from point X, okay? So Fy times L should be equal to mg times W over 2, where W here is the width, right? So Fy should equal to the weight times width over 2 times L, or m times g, so 14.4 times 9.81 times the width, which is 0.85, over 2 times L, which is 3.2. And if you plug in numbers, you find 37.96 newtons, which is about 40. Okay. So, okay, life's good. We figured it out and we got 5 marks from this. Okay. Part 2, the vertical component of the force of each hinge on the door is equal to half the weight of the door. Okay. Hinge Y exerts a force F on the door at an angle theta to the vertical as shown. Determine the force F and the angle theta. Okay, so this component is, the vertical component is F cosine theta, right? And the horizontal component is F sine theta. Okay. We found F sine theta earlier, right? Because this is what we did here. We found, show that the horizontal component of the force of hinge Y on the door is about 40 newtons. Okay, so this was the horizontal component, Fy, right? And Fy times L was equal to that, and we found Fy. So we can just write down Fy is equal to 37.96. Therefore, F times sine theta is 37.96 newtons. And then they tell us that the vertical component, F cosine theta, is equal to half the weight, so mg over 2. Okay. And m times g is, what was it? Wait, I'm missing. Yeah. So 14.4 is the mass. Okay, 14.4 times g over 2. So F cosine theta is 70.6. That looks like a lot. Did I mess up something? 14.4 times 9.81 over 2. No, 70.63 newtons. Okay, so we have two equations with two unknowns. If we divide them, we find that tangent of theta is equal to 0.537. So theta is 28.3 degrees. And then F, we can use any of the two equations. Let's use the first one, 37.96 over sine of 28.3 yields 80.2 newtons, and that's the answer. Okay. Okay, part 3, an identical door is supported by hinges that are much closer together. Explain how a smaller value of L affects F and theta. You should consider moments about point X. Okay. Okay, so let's consider, okay, the moment about point X, I mean, from this scheme is F sine theta times L, and that moment should be counteracted by the weight times W over 2. So we have the first moment is F sine theta times L is equal to mg W over 2. So the force is proportional to 1 over L. So if L decreases, F should increase, okay? And then we can also use that F cosine theta, the horizontal component of the force, is also mg, is mg over 2, which is what we wrote earlier here, okay? So this is the second equation, okay? In other words, the vertical component of F must equal the weight, right? So cosine theta, let me go back to black, is mg over 2f, okay? But remember that f is proportional to 1 over L, therefore cosine theta. So in other words, I'm sorry if I'm confusing you, but what we found now is that cosine theta, okay, is proportional to f, but f is proportional, is proportional to f to the minus 1, to 1 over f, therefore proportional to L. So if L decreases, cosine theta decreases, therefore theta increases, right? Let me quickly check with my calculator. Okay. Yes. Okay. So theta increases, and that's the answer. And I'm sorry it took me a while. This is the first past paper. This is the first Unit 1 past paper, and I'm a little bit rusty, but okay, I plan to upload more Unit 1 past papers, hopefully Unit 2, and hopefully the lessons on Unit 1 and Unit 2 will come soon. And also I plan to make more videos on this channel. Some of them might be unrelated to physics, but we'll see how it goes. So please like and subscribe, and see you in the next video.